Morning. I'm going to briefly go over a single hood system to start off the morning, even though we kind of went over that yesterday. But I think it may make it easier for us to have just a single video that'll cover all of this stuff and also a good warm up for what we're going to be doing with two hood systems shortly. Okay, so here's an example from the book of a single hood system. At the end, at point A, is a welder's hood, kind of a cone-shaped hood. It can be moved around on flex duct. Up to now, mostly we've been hanging around with galvanized iron. In this case, we're going to be working with flex duct, okay, which has a much higher resistance to airflow. Remember, the R for galvanized is designed is designated as 1. The R factor for flex duct is 2.4. So we're going to be using that to in our calculations of the resistance to flow caused by the flex dust. Okay, so basically it's got a hood at point A. It's got duct work. It has no filter, as many systems do. Just goes to a fan, and they don't show a stack here. In fact, this example in the book doesn't make use of a fan or look beyond the suction of the fan, but we're going to add on a stack so we see a complete system, except of course for the filter. Okay, so I'm going to go ahead and take a look at this. Now, they gave us the hood loss factor, K, which is 0.25. Okay, and they gave us an elbow loss factor to use, 0.27. Assuming a four-piece elbow. If they hadn't given it to us, we would have gone to our tables and looked it up. Okay, so for instance, here's chart 11 is where we would look up the various K factors. That's this column here for the various different kinds of hoods. And if you're going to design a system have one hood in it, you could just choose one of these alternatives or something that you found somewhere else. For instance, you could, if this was hanging over a vat of warm solution or liquid, you might have this receiving a canopy hood like this one. And here are different calculations, different ways to calculate what the area and loss value would be for that particular hood. So now, instead, if you have and one of the simple hoods that we were working with, here are the K factors for various of them. Notice the bellmouth hood has got the lowest K factors, the most efficient of these hoods. So at any rate, so you can choose a different one if you want, but they gave us this information on this one. So that's the K. That's where we get the K factor. We use different hood. As far as the material is concerned, the flex duct, that's in the roughness chart. Okay, and you'll notice that for galvanized iron, it's 1.0. For in the range that we're working, probably usually 2,000 to 4,000 feet per minute. And for let's see if we have for flex duct, it's 2.5, 2.6. They use 2.5, I think, in their calculations. Okay, so I'm going to get that out of the way. And we have 25 feet. We have a 90-degree turn with a radius of 1.5, a ratio of, let's go into the elbows. That's a 90-degree turn. Okay, here's our 90-degree turns, and it's a 90-degree turn with a four-piece with a radius of 1.5. So it would be, as they gave us, would be 0.27. If they don't give it to you, you can always look it up on here. Okay, so we'd be using 0.27 for the factor for the radius. Now, R over D means the radius over diameter. In other words, R over D of 2 would mean it's a 6-inch duct with a 1-foot radius to the middle of the curve here. So that'd be 6 inches in diameter of the duct itself, but the radius of the curve that it's making is twice as much, a 1-foot radius. And you can see it a little bit clearer over here. That's pretty good. You know, you might get much tighter 6-inch and a very tight 6-inch and 1, something like that, which would be a higher resistance factor. Okay, and the worst case 90 degrees. Now, if you have a 45-degree angle four-piece in the same situation, you just divide that in half. Okay, so, and you do that for each elbow. You would do that calculation. So I'm going to go ahead, and this is what we need for this particular system. And one of the ways that we might summarize this is to put together a chart which shows all of our losses and factors. Okay, so for this one, they told us that the hood factor is 0.25. So I'm going to see. Let's see. They told us that what we need 1,000 cubic feet per minute of the air exhausted. That's our Q. We need a transport velocity to keep the particles moving through the duct of 3,000. That was given to us again. If you don't have it, you can go to the chart. Okay, let's go to our charts again. Okay, chart 11 again for a bell-shaped hood, we would calculate the Q value using one of these two formulas. Okay, I usually use this one, which is the AIJ modified formula. Okay, and or you can use either one. You can justify either one if you want. And to get the transport velocity, we would go to, let's see, I think it's in chart 9. So chart 9, transport velocity. So depending on the particle or the material you're trying to move, you would choose different transport velocities. Fine dust might be 3,000. That's what it looks like we're dealing with here. So transport velocity is 3,000. The length of the ductwork that we're dealing with, in this case, is 25 feet of flex duct. So let's go back to that. Okay, we have 25 feet of flex duct. And this is just a chart where I'm summarizing the data that I have. The hood factor, I think, was 0.24 that they gave us. Let me get back to that. 0.25. And the elbows, there's a single elbow, and the loss factor for the elbow from that chart, or from what they give you, is 0.27. Okay, we don't have any branches or keys, in other words, places where we have a second hood joining this. And we're ignoring system effects. System effects are usually other kinds of locations where you might have unusual conditions of turbulence. For instance, if you're connecting to the fan in a kind of a plenum or a box and has to change direction at the same time that the fan is spinning the air, and so on and so forth. For the most part, we're going to ignore system effects. If on your project you have an idea from a manufacturer of a fan that mentions system effects and how to calculate them, or what the K value might be for them, you can include that. And if you have other factors, such as maybe a filter being present. In this case, we don't have a filter being present. So we don't have a K factor for a filter. That you would probably get from the manufacturer. Okay, so we're going to use these values. We're going to actually calculate the losses in this, the losses and the pressures and the size fan that we need for this particular system. Okay, let's go back and let's get into our calculations. Okay, here we go. Okay, so now the way that these charts work is we literally start from the point that says start here. Okay, now this part over here is for situations where we're going to be coming from a previous junction into a new part of the system. We don't have that here. We have a single hood and a single system from a hood to a fan and up a stack. Okay, so in those situations, we're just going to use the two adjoining columns of this single spreadsheet. Now, if we have a more complicated system, we're going to be using these two and then going on and creating another two for the next junction, another two for the next, and so on until we get to the exhaust stack. Okay, so let's take a look at what I have to do. So start here. Number one, where am I coming from? Well, I'm coming from a hood. So if I put a 1 in here, this system knows all the calculations will be appropriate for a situation where you're coming from a hood. And where are you going to? Are you going to a junction or to a fan? Well, we, in this case, are going to a fan. There's no junctions in this system. Okay, so if you look at the diagram, okay, we're going from point A to point B, the suction of the fan. Now, the second column, you'll notice that I actually added that on. And in this case, it's asking, okay, where are you coming from now? Oh, okay, well, this time we're coming from the fan itself, the suction of the fan itself, and we're going out of the stack. So if I were to draw it on here, B would be here, and C would be at the top of, say, a 10-foot duct coming out of the fan. Okay, not shown there. We're adding that on because we want to make sure we know the whole process. Okay, so the desired flow rate that we need from our spreadsheet, what was that again? Okay, let me get back to it. smaller so I can see it. So our desired flow rate is 1,000 cubic feet per minute. Our duct length is, how long is our duct? Our duct is 25 feet. Our flex duct is 25 feet. Our target velocity is 3,000 feet per minute. Our duct roughness for a flex duct is 2.4, as we looked up before. Okay, so now the next thing we have to, we don't have any slots in this system. So if we had a slot, we would change this, but we don't. We only have a cone type hood. So we're not going to put, we're going to leave this at 0. Okay, so we would put in the velocity, slot phase velocity, and the length of the slot if we were working with a slotted hood, but we're not. Okay, so now acceleration factor. If we have a hood, we put 1 for the acceleration factor. If we have no hood, we put a 0 in there. And the formulas below will adjust to accommodate situation where we're starting from 0 static pressure at hood, or or if we're coming from a junction where there's no hood involved. Okay, so now a branch entry. We don't have any system effect we're going to ignore, and we don't have any other K factors. If you had a K factor for a filter, we would put it here in other. So the total K factor is, well, I missed a couple there, didn't I? Okay. We have 1 for the acceleration factor. Now the duct entry from the K for the hood itself was 0.25. I think we looked that up. They gave that to us. Oh, that should have been 0.25 there. Okay, just to confirm, I'm going to go back here and take a look. Yep, it was 0.25. Now the K for the elbow was 0.27. That elbow, that 4-piece elbow that made our 90-degree turn, was 0.27. If we had 2 elbows, we would have doubled, 2 identical elbows, we would have doubled that, made it 0.54. Or 3, we would have tripled it, and so on. We count for the loss at each elbow. So this entire section is our accounting for various losses throughout the system. Okay, so next we're going to fill in the static pressure from, okay, static pressure if we're coming from outside from a hood is going to be 0. And so the sum of all the static pressures at the starting point is 0. Okay, so now the system has done a calculation for us. And we see that the system has decided that the duct diameter that you would need in order to get your transport velocity correct, in other words, to pull 1,000 cubic feet per minute through a duct and achieve 3,000 feet per minute, pretty simple calculation, Q equals VA. It's calculated that that has to be 7.8 inches, 7.8 inch diameter duct. Obviously, it's not a standard duct size, so we have to choose either 7-inch or 8-inch. Okay, so we get the choice now of putting that in designer's choice. It filled in for us 8. Problem with 8 now. Since the duct is larger, we're not getting our 3,000 feet per minute anymore. So now we have to make a judgment at this stage. Is the transport velocities for those particles happen to be basically a situation where they have a certain safety factor built into them, and they're kind of general. So the coarseness of the particle, the weight of the particle, the size of the particle, is not that well described, not that thoroughly described. So you can make a judgment and say, I know I was aiming for 3,000, but I think 2865 is going to be close enough and stay with an 8-inch duct. If you don't think that's going to work and you think you need the 3,000 feet per minute, you can change the duct diameter to 7-inch duct. And when you hit enter, you see it adjusts the duct velocity much higher. Okay, I'm going to stay with 8 inches. I'm going to say I think we're going to be okay at 8 inches. Now, when you do your duct work, you're going to have your own judgment about whether or not you think that this is going to be working out for you. Okay. Hi, Fanta. I think you just logged on. I think that you can probably see my screen and hear my voice. At least I hope so. Okay, good. I'm going to continue then. When you download this, you'll be able to back up and see where I was working. But I'll be going through a lot of this when I go into the next duct system as well. So this we're going to repeat this literally 3 times. Yeah, with a little tiny bit more complexity each time we do it. But you'll get a second look at it now, and you'll be able to go back over this as well. Okay, so at any rate. So we're done there. Notice it calculated for us the hood static pressure, the coefficient of efficiency. It did all sorts of calculations for us. Okay, so now the next thing I'm going to look at is what's going to happen when I go to my next section, which is going to be, it's going to be from my fan to my outlet. Okay, I put 3 in here because I'm coming from the fan and I'm going to the stack outlet. Okay, so I put in a 3 here. So you just follow this down. If we're coming from a hood, we would put a 1 in there. Coming from a junction, put a 2. Coming from the fan, we'll put a 3. And since we're going to not a junction but the stack outlet, I'm going to put a 1 in there. So now we still want the desired flow rate of 1,000. Okay, this time we have how much duct? How much duct was in that? We said on the dish we're going to make our own. It's not actually we added our own. So this is uncharted territory. Okay, so we said we're going to make our stack 10 feet long. So the height of the stack that we've added is 10 feet long. It's not in the original diagram. Okay, let me show you the original diagram again, if I can. Maybe it's better to get to it from here. Oh, there it is. I see it. Yeah, it's going to be right there. Okay. Remember, there was no stack here. We added a 10-foot stack on the other side of the fan. You can also go through the description of this in the book as well. Okay, I made a couple of changes. Like now, I'm adding a stack to it to make sure we know how to design a complete system. So the duct roughness that's going to be galvanized, not going to be flex duct. So the duct roughness is 1 instead of 2.4. Again, there's no slot or anything like that. We're not coming from a hood, so this time I put in a 0 for the acceleration factor. No hood is 0. There's no other losses other than what's introduced by the length of the duct, which we've already counted for by identifying its roughness and its length. Okay, the static pressure that is going into this system is calculated on this side. It was 1.74, so 1.75 winds up here. Okay, we type that. We have to actually put that in 1.74. Okay, and I hit enter. And again, it comes up, suggests a duct diameter of 7.8. That's no good for us. I can basically, on this side now, if I want to continue transporting those particulates, I better keep this at 8. Okay, now, when I do that, okay, it calculates for me the fan total pressure and the fan, the motor horsepower that I require, and the actual work that in horsepower that the system is doing, the moving air. Okay, this is assuming, and this is kind of general. You could get different ratings for efficiency from a particular manufacturer, but they suggest, in the text, Jeff Burton suggests you use zero point 0.6 for the mechanical efficiency, and so on and so forth. And for the safety factor, 1.33. So you got plenty of safety factor there. And so that's the fan that you would need. Fan that'll deliver 3.64 inches of fan total pressure and with a 1.5 horsepower motor. So we've calculated all this. Now, had there been a filter here, by the time we got to this, by the time we came, if there were a filter, it would be in the way here. So it would take the particulates out before they got to the fan. So now we don't need that larger transport velocity. So I could say, give me a 10-inch duct instead. If I use a 10-inch duct, the air is moving through there much slower on the exhaust stack, but there's no particles left in any way that we have to control or transport. And notice we save a little bit on the fan total pressure and on the horsepower that we need to run this, the amount of energy that we need to run this system. Okay, so the other thing that isn't obvious here is it becomes much quieter as well. And that's a consideration since it's likely that this stack is going to be outside your facility, and there may be some complaints about noise if you got neighbors nearby. Excuse me. Okay, so I'm going to move on to the next one. Okay, Fanta, did you catch most of that? I'm going to post these on Blackboard too as I save them as well. Okay, were you able to follow most of that? Okay, so now I'm going to move on to the next example, which is going to involve two ducts, two hoods. Okay, let me get to that. Okay, so let's see. Our next example. Let's see, single hood. Let's see. Where's my? Okay, here we are on Blackboard. Here we are on my notepad. I'm going to blow this up a little bit so we can actually see this. Okay, now this system is a bit more complicated. Okay, and the way that this system is working is that we have two hoods. We have a welding table, and we have a welding table with a sides and so on and so forth, and we have a separate welding table, I guess, which has a flex duct connection to it. We have an air cleaner, okay, as we will in most systems, and we have a fan. Now, in this case, we have a junction. We have a T or a junction. Happens that it's a 45-degree angle. That's going to be important to us. Okay, so this 45-degree angle to this junction is going to come up in a second. Okay, so I'm looking at our welding table A. Okay, so our welding table, okay, we have a hood on this welding table. Air is being pulled up through here to C, which is our junction where this other welding table with the flex duct is connected. So we have a junction or a T here at C. So we have one main system from A to C, and then we have a branch that joins up to it from B to C. Okay, so that's going to be the first part of our calculation. So I'm going to worry about that. I'll come back to the rest of the system. We're worried right now about going from A to C and we're going from B to C, and then we'll get on with the calculations that we need. Okay, so let me go back to double hood systems. Okay, here we go. Just like before, I'm going to start at the point where it says, literally, start here. I'm going to start at the top of the table. Now notice that we've duplicated our spreadsheet here, and then there's another one, the second one here. This is worksheet 2 of 2, right? And so there's two of these spreadsheets now. Okay, so this first one is going to take care of that section from A and B to C. Okay, so I'm going to start here, and I'm going to tell it, well, where am I starting from? Well, let's see. This particular run is going to be from B to A to C, right? So we're starting from a hood, right? So I'm going to put a 1 in here to let it know we're starting from a hood. And where am I going to? Am I going to the fan? Am I going to a junction? No, I'm going to. You're never going to go to a hood to another hood, so they don't bother putting that here. Okay, you're never going to a hood. Okay, so where's it going to? It's going to the fan directly, like a single hood system, or is it going to a junction? Well, in this case, it's going to a junction, so we fill in a 2 there. Okay, so our first run is from A to C, from that first hood to that second hood. Okay, so we're looking at A to C. Too much information. I'm going for that from that first hood to from that first hood to that junction C. Okay, so let's do the calculations for that. Now, as it happens, okay, let me see if I can't open this up. As it happens, they have taken this table and filled it in for us. You would have to do exactly the same thing. From A to C, the Q value, now you could look this up on chart 11, or they might give it to you in a problem. The Q value is 2,400 cubic feet per minute. The transport velocity that we want for the fumes, the metal particles of fumes that we want is 3,000 feet per minute. And as it happens, they're telling us that the distance from A to C, remember this is run A to C, is 25 feet. Okay, now I know right away that I need to look up a K value for the hood. So I would go to chart 11, or if a manufacturer gave it to me, I would look that up, and the K value happens to be 0.25. Okay, so now I'm going to go here to our welding table. Excuse me. I forgot one thing. There is a single elbow here. Okay, now depending on what kind of elbow I use, well, as it turns out, they told you all elbows are K equals 0.39 given by the fabricator. That sounds like it's a pretty severe angle, like maybe an R1 or something like that, or maybe only 3-piece or something. But you could either get it from the manufacturer, or you could look it up on the chart that we looked at before. Where I think that was chart. I can look at. You'll see which one it is. It's actually notated. I think it was chart 9. I'm not sure. So at any rate, no, I think it was maybe 12 possibly. So at any rate, you would get that from, so it's a single elbow, and the K factor for that style elbow is 0.39. Had there been more than one, we would have actually added those together. In other words, if there were two, we would have said 2 times 0.39 or 3, and so on and so forth. So the kind of duct it is galvanized. So we're going to use an R factor of 1 for galvanized iron duct, round galvanized iron duct. Now, there is no T because we're looking at that as the main ductwork. We usually figure the T issue with the in the branch ductwork that's connecting, so we're leaving that blank, and we're ignoring system effect factors, okay, as we talked about on the first duct that we just talked about. Okay, so now from B to C, things are changing. Now, this particular hood needs 1,000 feet per minute, but it still also needs 3,000, 1,000 cubic feet per minute, but it also needs a transport velocity of 3,000 feet per minute. Okay, it's also approximately 25 feet long. The hood factor, which is given to us here, but we could look it up on chart 11 if we don't know it, or get it from the manufacturer, is 0.5. Okay, so there's no elbows here. It's going directly into the junction, okay, or T or junction. There's no elbow, so we ignore that. There is a T. Okay, there is a junction, and we looked that junction up on our chart. Okay, they say 0.28. Let's see if they get the same thing that we get for that. Okay, I'm going to go back. Okay, and let's see where our T branch junction. Okay, so if I have a 45-degree junction, right, the K factor that they're suggesting that you use is 0.28. If you don't have one that's given by the manufacturer, I would go to this chart in order to determine what the K factor is going to be. So I'm going to use 0.28. Or I'm going to use, what did they give me? Oh, they gave me the same thing, 0.28. They probably got it from the same table. Okay, so if they give it to you, it's great. If not, so this is flex duct. So our R factor is not 1 like for galvanized iron, but it's 2.4. Okay, so we got all the information. Now we need to go back to our spreadsheet to do these calculations. So from A to C, we want a transport. We want to have 2,400 feet per minute from our chart. We need 25 feet of duct. Our target velocity is 3,000. Our duct roughness is 1. There happens to be a slot in here, right? And again, this would come from chart 11. Okay, the length of the slot, there's actually 2 5-foot long slots, I believe. Okay, there's 10 feet of slot, and desired slot velocity is 2,000 feet per minute. Now, if you don't have a slot, without a slot, you just put a 0 and a 0 there. You don't have a slot calculation. Okay, so the acceleration factor, you're coming from a hood, not a transition, so you put a 1 in there. Our duct entry from chart 11, 0.25. Our elbow K is 0.39. Had there been more than one elbow, we would have multiplied it by the number of elbows. No branch entry. We're on the main duct. No system effect. There's no other factors that unusual factors like maybe a filter that might give us resistance to flow. So we put a 0 in there. The total K factor is 1.64, which is going to be used. You don't fill that in, it calculated it for you. You could have it could have made you add it up, but you didn't have to bother. If you use the hand chart, which is laid out exactly like this, you can see the formulas on the side that you would use to do these calculations. Static pressure from is 0 because it's coming from outside air. Okay, so now it's done our calculation. The ideal duct diameter is 12.1 inches. Okay, we select 12 inches, which is a little bit less, so we get our full 3,000 feet per minute from this particular size duct. Okay, and it calculated various other things, including our slot static pressure at the junction. Okay, the hood static pressure is 1.42 inches. Okay, minus 1.42 inches. Okay, it's under suction, and our static pressure at our junction is 1.93 inches. Okay, right now, but we're going to find out more about that in a second. Now we're going to do our second run, the junction. That is going from B to C. Okay, so now in this case, I'm also going from a hood, so I put a 1 in here. I'm going to a junction, so I put a 2 in there, not the stack outlet, but 2. Okay, so what do I need here? Well, this one we know we need 1,000 cubic feet per minute. We got 25 feet of flex duct, so we use a K factor of 2.4 here. We want 3,000 feet per minute flow rate, transport velocity, that is. Okay, our acceleration factor is 1 because we're coming from a hood. Our duct entry factor, K, is 0.5. That we either get from chart 11 or we're given by manufacturer. Okay, there's no elbow, so there's no factor in here for an elbow. But our branch entry effect, our K for our branch entry is 0.28. That's all taken in the branch, not in the main section, the first hood, the section from the first hood. Okay, so that adds up to a K factor for this particular run from B to C, okay, of 1.78. So this system automatically, the from static pressure is 0 because from outside the hood it's 0, okay, or at A it's 0. Okay, so in this particular hood, it finds that we need an ideal duct diameter of 7.8. Okay, so 8 is the closest standard size to that. So we put an 8, we lose a bit of velocity. So we have to make a judgment. Is it going to be enough to transport these welding fumes? Welding fumes are very, very tiny particles. So I'm going to say, if it had been 2,500, I might have been a little concerned, but I think we're less than 5% short on our duct velocity. I'm going to stick with that. Okay, so it goes ahead and calculates our actual duct velocity, our velocity pressure, our static pressure at the 2 point. Now notice, static pressure at the 2 point for both of these runs, that's the same point. So it's a problem. If this one, the static pressure we have coming from the one hood to C, at point C is 1.93, this one's a little less than that. There can only be one static pressure. Okay, so we're going to assume the higher of the two numbers, the higher static pressure, is the governing static pressure for our subsequent calculations. So we want to keep that in mind. The other thing we got to keep in mind is we don't want this to just be, completely different, because we're going to get all sorts of system loss effects and problems here if these two are supposed to be the same, but they're so different. Well, in fact, they calculate a ratio for you of here's the ratio of the static pressure effects. Okay, if I go across here, it's okay for the ratio to be between 0.8 and 1.2. If they're so different, it's not going to work as well. Okay, so it's 1.03, we're in good shape. Okay, and governing static pressure, usually take the higher value. So they're suggesting you take 1.93. So now we can take, because of the size ductwork that we chose, the amount of air that we're pulling through here is, and the junction, and the effects of the junction, the amount of air that we're pulling through here is 2,400 cubic feet per minute from one hood and 1,014 feet cubic feet per minute from the other hood. So our total Q going through that junction is 3,414 cubic feet per minute, a little bit more than a little bit more, a little bit less than when we were literally originally thinking we would get, which was 3,400, right? But we got a little bit more in the actual amount because of the duct sizing and so on and so forth, the acceleration effects. We actually wind up with 34. That's so we know our actual static pressure at the junction. We know the actual amount of air that's going through there as well. Okay, cool. So now we're going to take that, we're going to duplicate that spreadsheet, and we're going to go down to this second spreadsheet, and we're going to analyze this thing from point C. We got a couple here. We want to go from point C to point D, right, which is going to include a lot of galvanized iron ductwork, which is in that chart that we showed you at the beginning. I'll bring it up again. We got some galvanized iron ductwork. We got an air cleaner or filter, and we got 1, 2, 3, 4, 5 elbows between C and D. And then finally, we want to go from D to E, which is from the fan suction to the exhaust stack, out of the exhaust stack into the open air. Okay, so we're going to do that in our next two rows. So we're going to pick up. So first thing I'm going to do is I'm going to put in here the Q values for the previous run, 2,400 and 1,014, and the velocity pressure in the main system. Okay, what was it? It was 0.58. Let's see if we can't find that here. 0.58 duct velocity pressure in the main, A through C, at C, and in the branch, A through C. Okay, so I'm going to move those down here. So our velocity pressures. Okay, so now I'm going to look at, by the way, in the book, he doesn't bother to fix these. They're wrong in the book. We're actually doing the run from C to D here. He keeps showing us the A to C. He doesn't bother to change them for some reason. I think he neglected. I think it was a typo. But at any rate, so we get 3414 is the amount of air that's going to run through the rest of this system, right? No more branches here. It's going through here, and then it's going through here. It's not going through both at the same time. It's going to be the same volume going through both. The amount of ductwork that's in the run from C to D is 40. That was given to us in the length of ductwork. The duct roughness, galvanized iron, is 1. Our elbow coefficient was let's see what our elbow coefficient was. Did they give it to us? Our elbow coefficient was 0.39, but we have 5 elbows. So it's 5 times 0.39, which comes up to 1.94. Okay, that's in there because that's a lot of resistance now because we've got 5 elbows in this system. You guys remember when we built our system in the lab, what adding on a lot of elbows did for us. Okay, so I'm going to continue here, 1.95. What other factors do I have here? Okay, well, in this section, let's see. I just have the elbows and the length of ductwork, which I already accounted for. So now that adds up to 1.95, and static pressure from. Now the static pressure from is from our starting point, which is point C, which we get from our previous calculation, 1.93. Our static pressure from, what was our governing static pressure again? Was 1.93, right? Okay, so the higher the two static pressures at that junction. So we put in 1.93 there. Other static pressures. Well, we got that filter. That filter, the information we get from the manufacturer on that filter may give us a static pressure in inches that we should include within a certain velocity, or it may give us a K factor. So if they give us a K factor, we put it here under other Ks. In this case, they gave us the inches of water resistance that we would get from that filter within a certain range of velocities. So we put the 4 for the filter in here. The total of all the static pressures is 5.93, okay, that we know of, and the total K is 1.95. And the system does a calculation for the rest of it. The ideal duct diameter turns out to be 14.4. We're going to select 14, which gives us a velocity of 3194. I forget, what did we say that we needed? We said we needed 3,500 transport velocity. We needed 3,000. That's pretty high, actually. However, to go to 15, if I go to 15 here, okay, that's pretty, that's like 10% under, so I'm not so sure I want to go to 15. I'm going to stay at 14. Okay, you have to make kind of a judgment about this. Okay, so now here's our actual duct velocity. Here's our duct velocity pressure, so on and so forth. There's no hood involved, so there's no hood static pressure. Now our total static pressure at our our two location is the fan suction, is 7.66 inches. Okay, so pretty soon we're going to want to compare that for the rest of the system. So now we're going to go, so it's total 7.66 inches. Okay, so we're going to go up here now, and we're going to look at the section from D to E, which is, if I go back to the picture, D to E is from our fan suction, which was 7.6 inches or something like that, and out up 10 feet of ductwork, or whatever, how many feet of ductwork they say? 20 feet, D to E, 20 feet of ductwork, our stack. Okay, so it's going to go 20 feet of ductwork, and it's galvanized, 1 point. Okay, so I'm going to go in here. So now our desired flow rate is still the same, 3415. Our duct length is 20 feet as it happens. Okay, our target velocity is 3,000. Our duct roughness is 1. And I'm going to go down here to, let's see, static pressure from is going to be, well, this is coming from this calculation. And so our static pressure from is 7.66 inches. Okay, because this is coming from that point. Okay, so now I continue up. There's nothing else for me to fill in here. I think that's it. No elbows or anything like that, just straight stack. And finally, we wind up with our total system is going to, we have all the calculations for our total system. Our fan total pressure is going to have to be 15.52 inches. That's some of the pressure in and out. Okay, our fan, it's going to be 8 horsepower, and we're going to need a 21 horsepower motor in order to accommodate that. Now, one of the things I might do is, since I'm downstream of the air filter here, I might say, let's go to a 16-inch duct. See if that helps us out. Okay, and in fact, it drops the horsepower a bit. Okay, and let's see, 20 feet. I think that's it. I think we're done. So you can use this system. Let me just make sure I got all this in. Static pressure from. Did I tell it static pressure? Static pressure. Static pressures. That's the from. Of course, 2 is going to be 0 because it's a stack. Did I tell it was a stack? Yep, stack output. So it knows that the discharge pressure is going to be 0. Okay, so that's it. We're pretty much done with that. So you have all of the different factors that you need to design your 2-hood system. Okay, so now I'm going to do one more with a little bit more complexity. Okay, so you'll be able to go back over this. And if I made any mistakes going through this, I'm really charging through this pretty quick. If I made any mistakes, you can send me an email, and I'll send out an update. And of course, I'm going to save this so that you have this file completed so you can go back over it. I'm going to close that. And I'm going to go to the next hood. Okay, and this one's going to add a layer of complexity, and you'll see why. Okay, which you may run into if you have a simple system, you may not run into this issue. Okay, so here's our system again. A little bit different. It's a grinding hood of some kind. I don't know exactly what it's supposed to look like. A booth hood. We have 1, 2, 90-degree elbows between A and C. There's a junction at C. We have a 90 and a 45 here. We have a 90, 90, 90, 90, 590s going through a cyclone air cleaner. Usually this does the pressure drop across these is a bit lower than it is across a medium filter. And then we have a stack. And here's a summary of all of these factors. Okay, now let's see if there's anything unusual here. Here's our T factor, which goes in the section, the branch B to C. Our elbow loss factors, you get them by adding things up. This really high one, 2.0, is because there were 5 elbows, each at 0.40. The T goes in at 45 degrees, so we know from before that it's the same 0.28. I'm wondering how about there is something that I was looking at here a moment ago, and let's see. Nope, that's it. That looks like about it. Okay, and what about the lengths of ductwork? We have for run A, we want a 3,000 cubic feet per minute, a lot of air. We want 3,500 feet per minute velocity. B through C, we want 2250 cubic feet per minute, 2,000 feet per minute velocity, 20 feet of ductwork, 15 feet, so on and so forth. We haven't calculated C to D or D to E yet, the stack, as of this point. Okay, there's a few more details down there if you need it. They're telling us that the loss factor from the air cleaner, which is given by the manufacturer, is equal to 2. K is equal to 2. So we're going to put that in instead of a static pressure loss across the air cleaner before. Okay, and they asked us to assume no system effect losses with the fan. You can look up system effect losses in the book, and it'll describe to you when you might actually see them. Too many elbows is right. Yeah, really, that's a real effect, right? Okay, let's go and actually do this calculation now. Okay, so let me see. Let me go back here to hood system. Okay, this one's going to involve a correction. That's why it's a little bit more complicated. Okay, I start at the top, just like before. Start up here at the top, start here. I'm not really at the top. Start here. Now notice that we've copied this spreadsheet 3 times. There's going to be a correction involved in here. Okay, it's not as complicated as it looks. Just go through it. It's all linear. So you go through it one piece at a time. These are all filled in because nothing's happened yet. We start here. So from A to C, we're looking at run A to C and B to C, from the 2 hoods to that junction. Okay, so where are we coming from? Well, we're coming from a hood, so we put a 1 in there. We're going to a junction, so we put 2 in there. Okay, so from A to C, we want a desired flow rate of, was it 5,000? I don't think it was 5,000, was it? It was 3,000. So I'm going to change that to 3,000. Okay, and 3,000. Okay, 3,500. The other one's 2,250. Okay. Okay, so that's 3,000. And let me see if I can't get this to more, lay out my landscape here a little bit so I don't have to move around quite so much. Okay. Okay, so our length is 20 feet. Our target velocity is 3,500 feet per minute. Our duct roughness is 1 for A to C. There's no slots. I don't remember there being any slots. There's no slot. I'm going to assume there's no slots. Our acceleration factor is 1 because we're coming from a hood. Our duct entry, our K value from the hood, duct entry loss from the hood, is 0.5. And we got that from there. We have how many elbows we had? We had 2 elbows, I think, and they were both 0.4. So we put in a 0.8 for the elbow K, right? Since there were 2 elbows, we have to account for both of them. 1, 2. Okay, and our branch entry, we don't have a branch entry. We no system effect, and so on and so forth. So total K is 2.3. Okay, so now, actually, there is one that I'm missing here, isn't it? Well, actually, I'm not missing it yet because it's not in this section, the filter. So up to this point, up to C, we're fine. We got all the K values accounted for. Static pressure from is 0 because it's coming from outside the hood. Okay, so the ideal duct diameter it's suggesting to us is 12.5 inches. So, okay, let's try 13 inch. Okay, well, if we use 13-inch duct, we would have an actual transport velocity of 3,255 feet per minute. It would calculate and do all the rest of the calculations. That's the last slot that we can actually fill in ourselves. And let's see what we have here. Let's see. Hood static pressure is going to be about 1 inch, and so on and so forth. Our actual velocity, actual duct velocity is going to be more than our that we need. So we got our transport velocity. So we're in good shape. Let's now move on to our next section, which is B to C. Okay, so let's go take a look at B to C. Okay, so B to C, okay, we want 2,200 cubic feet per minute, 2,250 rather. We have 30 feet of ductwork. Our target velocity or transport velocity is going to be 3,500 feet per minute. Our duct roughness is 1, okay, because it's galvanized iron. No slots. I'm going to move on up. Our acceleration factor is 1 because if you look over here, 1 is for hoods. Here we are coming from a hood. Our duct entry factor for a hood is 0.5. Again, you could get that from chart 11, depending on what kind of hood you're using. Now, elbows. Our elbow, let's see, K for our elbows is, let's see, elbows 0.6. Okay, that depends on the type of elbow that you're using. Okay, you would get that from the chart for elbows. The radius and diameter would influence that, and the angle would influence that. You know why it's 0.6? That's an interesting fact. Let's go back and look. Let's see. It's no, now you got that. It's 0.6. I guess it's just a very tight turn. There's only a single elbow there, just that one. Okay, and that's our. Oh, actually, it's a double. Got an elbow there, and they're actually showing an elbow here as well, 45-degree elbow there as well. So you have a factor for this elbow here, and you have a factor, half of the factor for this elbow here. So it would be, let's see, our branch entry, all elbows are 0.4. So we have the 0.4 for the 90-degree and 0.2 for the 45-degree elbow. Okay, and so that adds up to 0.6. So that's how we got that 0.6. Okay, so our branch entry factor, okay, which is depends on the angle of that entry. Okay, we got that from our chart for that purpose, is 0.28. Our system effect, we don't have any system effects. There's no other losses, no filter or anything like that in this section. So there's our total K for B through C. Static pressure starting is 0 because starting from outside a hood. Okay, and the ideal duct diameter would be 10.9 inches. Well, I think I can get away with an 11 inch on that one. It'd be pretty close to what our transport velocity is intended to be. Okay, certainly within a few percent anyway. So there we are. Transport velocity is going to be 3409. We had wanted, oops, did I make a mistake here? Transport velocity, oh, that's our Q. Transport velocity should be 2000. Let me go back up there. How come you guys didn't catch me on that? We don't have to be moving that fast on that one. Okay, so let's see what we wind up now. So now actually one of the things you can do with this is experiment with your design. Okay, so in this case, they're suggesting a duct size of 14 inches. I could go either with 14 or 15. And I get, let's see, I get my, so if I go with 14, which velocity is 2000. Target velocity is 2000. Okay, and Q is 2250. We go with 14, and I get a little above what I need, which is 2105. Since it's smaller, a little above what I need, which is 2105. But that's okay. I don't think I want to go to a 15-inch duct. I think it's going to be too low a transport velocity for me to tolerate. Okay, so now we've completed this, and this spreadsheet does the calculation for us, and it finds that the static pressure, the hood static pressure is 0.99 for one hood and 0.42 for the other. The static pressure where they come together is, let's see, where is it? The static pressure where they come together is, let's see, the static pressure at the 2 location, where both of them come together, from and to. Well, one is 1.75 and one is 0.79. Look how different they are. Now, remember, we have a rule. Here's the ratio of the static pressures. We want them to be between 0.8 and 1.2. And in fact, the ratio is 2.2. So I have a problem here, don't I? I need to find a way to increase the static pressure at that point for our branch duct. for this branch duct because it's too much lower than the static pressure from our main system. Okay, so one of the ways that I may do that is I could go back in here and try resizing this duct to 12. Okay, let's see what happens now. Okay, well now, what happens now is it increases my transport velocity in my branch duct to more than I need. However, that's okay as long as I have at least what I need. If I can tolerate a little bit of noise from the duct and so on and so forth, I have a higher transport velocity. But notice now that the static pressures, let's see if I can't find, static pressure at point C for A to C is 1.75. It's 1.75 from the main hood, the first hood. That's 1.51 from the branch hood. So now the ratio of static pressures is 1.16. So they are basically close enough. They're within 0.8 to 1.2. They're close enough for me to tolerate that difference in static pressures without not having too big a system effect at that point. Okay, so you guys got that? What I did here was I resized the branch ductwork so that the static pressure would satisfy this condition that the ratio of static pressures at the 2 point at C, where they join together, is no less than 80% or no more than 120% of what the larger one is. Now, the governing static pressure is always going to be a larger one. So from now on, when we move on to the next step, we're going to use the larger static pressure anyway. But at least they're close enough now that we think that this is going to work out pretty well. Okay. If it's a little bit opaque, I would use what you can do for the time being until it kind of sinks in is just use this exercise. Just use this situation. If you have a duct with this same situation where you see, where as you read this down, you see that the ratios are not good enough, well, you can increase the static pressure by reducing the duct size, okay, forcing it to suck harder, right? So you know that if you have this lower static pressure in your, if you have too low a static pressure in your branch, you can get that to be higher by reducing the duct size. And you can go from 14 to 13. I could have tried 13. I actually kind of eliminated stuff because I knew how it was going to come out. Well, 13 wasn't enough. It only went to 1.62. Let me go down to 12. Right? And there, now we're okay. The ratio is 1.16. So you can experiment with this. And that's really what this spreadsheet is for. One of the big advantages of using Excel, or spreadsheet programs on computers, one of the big advantages right from the start was the ability to do what if. What if I change the duct diameter here? And then have all the things recalculate on their own. Okay, so now our corrected flow rate, our total flow rate right at this moment, up to point C, through point C is 5418. Okay, that's 3,024.15, 2418 cubic feet. Our static pressure, governing static pressure is 1.75 inches. And we're going to go move on to now from point C to point D. Okay, from point C to point D, going through the filter and going also through 1, 2, 3, 4, 5 elbows. Okay, so let's go to our next one. So now we're going to, again, this is a second worksheet. You could have it on two different pages. You can have it on the same, cut and paste it onto the same page. Doesn't really matter. Okay, so this time we're coming from, start here. We're coming from, and actually I could actually paste this stuff in here now. Let me see if I can't find it. 3,024.18, just so we have it, 3,024.18. Our velocity pressure in the main. Okay, velocity pressure. Duct velocity pressure is 0.66 and 0.51. Okay, so now I'm going to go to our additional runs now. Okay, so now we are going to be going from, oops, did I jump up here or something like that? What did I do? Worksheet 1. Worksheet 2. Okay, so this is going to be from C through D. Okay, and this one is going to be from D through E. Okay, so let's see what we got. So our total Q, total amount of air that we're going to be moving is going to be 5418. Okay, and first I got to tell it I'm coming from a junction and I'm going to a fan. Put a 1 in there, not another junction. Okay, so let's see. I'm going to start here, 5418. The total length of ductwork that we have in this section, C to 3D, is 30 feet. Okay, the target velocity for this section, what was the target velocity here? It was always the same. Target velocity was, we need to keep things moving at the highest target velocity. So that's going to be 3,500. Whatever's in there is what we got to use, right? 3,500, that's good. The duct roughness is 1. The acceleration factor, well, it's no hood here. It's coming from a junction, so I'm going to change that to a 0. Okay, let's see. No, there's no hood. Elbows. Okay, now elbows we have. We have more than enough elbows there. Our elbow K factors are 2.0.
I think it's
And
2418
that's
instead of
5 at 0.4.
5418.
Okay, what about branch entries? No. System effects? No. Other K. Well, let's see. Didn't we have a filter in this part of the system? And I think they gave us a K value for the filter, which was 2. So I'm going to put that right in there where you would expect it to be in other. Okay, that other is actually a filter, so it adds up to 4. Okay, so the static pressure from, remember that was the governing static pressure from before. What was the higher static pressure from before? 1 point, let's see, governing static pressure was the higher of the 1.75. Okay, so I'm going to put 1.75 in there for the governing static pressure. Did I just say 1.75? I got distracted there for a moment. Yeah, 1.75. Okay, hang on a second. I see a question there. Okay, not 50. Oh, you want to know something? Desired flow rate is 2418. Was it 24? I thought the total volume, the total flow, remember, we've joined these two systems together, right? So these two systems joined together now in C, you're going to need the amount of air going through the actual flow rate, the amount of air going through the first duct, which is 3,000, and you need 2,400 joining it from the second one. So the total flow rate, total Q, is at the junction is 5418. Are we okay with that? Is that a yes? Okay, good. So that's where I got that from. That's the total flow. In other words, that's the amount of air that's the desired flow rate that's going through point C headed through the rest of the ductwork. It's got to satisfy both of those branches. One of them is 2418, the other one's 3,000. So that's a total 30 feet of ductwork, and so on and so forth. 1.75 is static pressure from that junction. That junction we know is 1.75 from our previous calculation. And it suggests the ideal duct size is 16.8. If I want to maintain my velocity, I choose 16. So this actual duct velocity is 3880. That's pretty high. I wonder if I could get away with 17-inch duct here. Okay, we want 3,500. That's so close to 3,500. I'm going to stick with a 17-inch duct. Okay, that the airflow, less resistance to airflow, save us some energy. Okay, so now let's see. It calculates all these other factors for me. The total static pressure, suction static pressure at the fan is 5.16 inches. We know those elbows, those extra elbows in that filter really had a big effect. Okay, so I'm going to go ahead to the next section, which is, okay, where are we going? We're going from our fan, which is 3, and we're going to our stack outlet, which for this column is going to be 1. Okay, so now let's see what we have. From D to E, the desired flow rate is going to be the same. We've got to move the same amount of air all the time. Okay, how many feet of ductwork do we have there? Let's see. So we had 12 feet of ductwork. So the stack is 12 feet tall. And what's our desired flow rate? What's our target velocity? You know, we got some flexibility there. Okay, because I'm going to leave it at 3,000. I don't think they bring up here what they suggest, but we've gone through the air cleaner. So presumably a lot of these materials have been removed. I'm going to take a judgment call and just leave it at 3,000. Okay, so now as our target velocity. Okay, I don't necessarily have to go the same speed as the target velocity through the rest of the ductwork. Duct roughness, galvanized is going to put a 1 in there. Acceleration factor, it's going to be 0. I'm not coming from the hood. Okay, duct entry, no, there's no hood. There's no there are no elbows. There's no branches. Okay, system effects. This is a little bit of a debate. It depends on how the hook is, how the fan is connected. If it has a box that comes in the side and turns that going into the fan and so on and so forth. If there's a sudden turn coming out of the fan, there's a fan box, and it forces a sudden turn or something like that. That would have to come from the fan manufacturer, possibly, or you have to make a judgment at it. Again, you can go to the book. I will say, for our purposes, you can ignore system effects at the fan. Okay, so I'm not going to put anything in there. The static pressure from. Okay, what's the static pressure from here? Well, the static pressure from here is the static pressure at the fan, which is 5.16. Okay, the static pressure to is the same thing to the fan, the same thing as static pressure from the fan. Okay, so we come up with that. Ideal duct diameter was 18 inches. I'll go with 18 inches, see what we get. And we wind up with the rest of our calculations. Our fan total pressure is 10 inches. Our horsepower of the motor that we need to run this thing is 22 horsepower. And the actual work that it's doing is 8.7 horsepower. So we have all of the calculations completed. We could actually describe all of the pressures, static pressures throughout this entire system. So we did 3 different calculations here. First, I'm going to save this also so you guys can download it and play with it with the same numbers that I used. Okay, so we did the same thing for 3 different systems. The first one that we did was, let me see if I can't go back to it. The first thing that we did was a single, we added a stack to this. You don't see the stack on here. Was a single hood, no filter, just to a fan and an exhaust stack. Okay. The second one that we did was a 2-head system. We did all calculations for it, and it helps to do this summary before you get started. So you don't have to go back and forth to the charts all the time. Okay. And the second system that we did was a 2-hood system where, as it turned out, we got lucky, and the static pressure for this duct at C, for this part of the system at C, and this part of the system at C were close enough that we didn't have to make any corrections in the size of the branch duct. Okay, and we could just go ahead and then do our do our calculations C to D and our calculations D to the exhaust stack. Okay, so it's pretty simple for us. It wasn't simple, but it was pretty straightforward. Let me put it that way, for us to do that one. And the third one that we did was a two exhaust hood system. Whoops, going the wrong direction. It was a 2 exhaust hood system where we didn't get that lucky. We didn't get lucky. What happened was that the static pressure that we needed to run this hood at junction C was much higher than the static pressure at the original transport velocity that we wanted for the smooth hood B. So there was a big difference between the static pressure here and the static pressure on our grinding hood. You can imagine if it's under suction, you might pull some air back. There'd be all sorts of turbulence here. So we needed to adjust the size, diameter of this ductwork so that we got a higher velocity and a lower static pressure at this point. So we experimented. We changed the diameter of this ductwork until we got the 2 calculations for static pressure to be between a ratio of 0.8 to 1.2, between a minimum of 80%, 20% low for the branch, or 20% high for the branch. So they were close enough. And from that point on, we started again and we did a calculation from C to D, including the elbows, the lengths of the ductwork, the roughness of the ductwork, and whatever the air cleaner was contributing, either in static pressure from the manufacturer or the K value for it. And then finally, our last worksheet, we did from D to E to determine what the fan horsepower was going to have to be and what the fan total pressure was going to be. So it was a little complicated, but with these spreadsheets, if you go through the spreadsheet, remember this is a the air. Just think about how the air is moving. The air is moving in one direction. Everything's happening. This happens, then this happens, then this happens, then this happens, then this. It's all linear. So if you go through the spreadsheets in a linear fashion, entry by entry by entry, and make the right judgment at each point, the spreadsheet will then do the calculation for you. If you're interested in what calculation it's doing, you can click into that cell in the spreadsheet and see the formula that's using, what cell that it's adding or multiplying, and so on and so forth. Or even better, in the textbook, there is a chart that mirrors this spreadsheet, except it's meant for manual calculation. And if you use that, the formulas are right there. It tells you how to calculate, what formula you use to calculate static pressure based on the information that you've put in advance of that. Okay, so the only other thing is I'm going to put all this stuff on here, including, I'm going to put all of this up here, including the charts. Okay, these charts I think are the ones for what we did here. They're the ones that come up most recently. Chart 9 is for transport velocities for different kinds of particles. If you're dealing with vapors or gases, I would stick with maybe 2000 or something like that. With the roughness factors for say flex duct or for instance for galvanized iron, which is one. That chart 11 is the chart for all the hood K values that you can pick from. Okay, and you can find your own if you want to. Chart 13 is the values for the loss values for the elbows. Chart 14, that's where our branch entry was. Really, what governs the K value is really the angle of entry. So that's how you would actually calculate that. Use that K value in the spreadsheet. Your spreadsheet actually calculates all the rest of that, the static pressure that you require based on that. Okay, but you don't have to do that. All you have to do is come to that chart for the K value if you use the spreadsheet. And finally, I included this, but I told you you could ignore it. This is system effect losses. And you can imagine if the fan is such that the stack just discharges straight out, you don't have to worry about a system effect. But if you had to put an elbow on here right at the discharge of the duct in order to turn it, turn it upwards or something like that, well, that between the turbulence from the fan and the turbulence from the elbow, that would have a significant effect, even beyond what you might expect for an elbow. So they call that a system effect loss. So you can actually calculate that or estimate that from the types of outlets that you might have, inlets and outlets you might have on a fan. Okay, but for our purposes, you can afford to ignore that. Okay, so I think we tortured you enough for this morning. Okay, and I'm going to upload this today along with these charts so that you can work with the charts separate of the book on your computers if you want to. Okay, so I hope that helped. Did it help? Okay, did that help you out a bit? Okay, I understand. This is a lot to absorb, especially if you're not. Yeah, I redid the one, so you don't have to worry about yet what we did yesterday, because I redid what we did yesterday on the beginning of this. Some of you tuned in a little bit late and fast. Yeah, well, the advantage of being able to record it is that you can now go through it, scrub through it, and stop it and slow it down. Unfortunately, I didn't want to keep you here till like 2 o'clock in the afternoon. So you guys have a good Mother's Day. and enjoy the good weather that we're having today as well. Okay, take care, guys. Bye.